हेलो दोस्तों, आई होप आप सभी अच्छे होंगे। आपने हमारी पुरानी वीडियो देखी होगी, आपको कैसी लगी हमें कमेंट बॉक्स में बताते रहिएगा। और आज हम चलिए शुरू करते हैं आज की अपनी नई वीडियो।
In the semiconductor devices, the flow of charge carriers is within the solid itself. However, at low temperature, the charge carriers are not free to move as they do not possess sufficient energy to move. The charge carriers can be freed to become mobile charge carriers in a semiconductor by heating, applying a small voltage, or exciting through light. Use of semiconductor devices has many advantages, such as they are small in size, they operate at low voltages, they consume less power, they have long life as the solid-state material is durable, high reliability as they are less prone to microphonics. To fully understand semiconductor devices, it is important for us to understand the classification of materials on the basis of their electrical conductivity. We have learned that electrical conductivity or specific conductance is a measure of a material's ability to conduct an electric current, whereas electrical resistivity, also known as specific electrical resistance or volume resistivity, is a measure of how strongly a material opposes the flow of electric current. Solid materials are broadly classified into three categories on the basis of their electrical conductivity or resistivity. These are conductors, semiconductors, and insulators. Conductors have very low resistivity and high conductivity. Their resistivity ranges between 10 raised to the power minus 2 to 10 raised to the power minus 8 ohm meter. And in particular, metallic conductors possess conductivity in the range of 10 raised to the power 2 to 10 raised to the power 8 Simon per meter. Some examples of conductors are copper, nickel, etc. Insulators have very high resistivity and very low conductivity. Their resistivity ranges between 10 raised to the power 11 to 10 raised to the power 19 ohm meter. Their conductivity is in the range of 10 raised to the power minus 11 to 10 raised to the power minus 19 Simon per meter. Some examples of insulators are wood, rubber, etc. Semiconductors have resistivity and conductivity which lie in between that of metals and insulators. Thus, they have lesser conductivity and higher resistivity than metals, and higher conductivity and lower resistivity than insulators. Their resistivity ranges between 10 raised to the power minus 5 to 10 raised to the power 6 ohm meter. They possess conductivity in the range of 10 raised to the power 5 to 10 raised to the power minus 6 Simon per meter. Some examples of semiconductors are silicon and germanium. These semiconductor electronic devices may be made up of different types of semiconductors, such as elemental semiconductors or compound semiconductors. Elemental semiconductors are single elemental semiconductors. They belong to the fourth group of the modern periodic table of elements. Silicon and germanium are the most commonly used elemental semiconductors. Compound semiconductors are formed by using two or more elements. They are synthesized using elements from groups 2 through 6 of the periodic table. Compound semiconductors may be further divided into different types, such as inorganic compounds like cadmium sulfide, gallium arsenide, cadmium selenide, etc., and organic compounds like anthracene, doped phthalocyanine, etc., and organic polymers like polypyrrole. polyaniline, polythiophene, etc. You have learnt that materials are classified as conductors, semiconductors, and insulators based on their electrical conductivity, which in turn depends on their atomic structure. For example, copper is a conductor, silicon is a semiconductor, and wood is an insulator. According to Bohr's postulates, every atom consists of electrons that revolve around the nucleus in fixed energy levels, called orbits or shells, and the angular momentum is quantized for each electron. The orbit number in which they revolve is characterized by the principal quantum number. The concept of fixed energy levels is valid only when an atom is well isolated from other atoms. This is not possible as atoms are closely packed, especially in the case of solids, and thus there are interactions between the atoms. Due to this, the outer orbits of some neighboring atoms come very close and even overlap. Hence, in the case of atoms in a solid, the electron energy is affected due to this proximity of neighboring atoms. It should be remembered that each electron still has a distinct quantum state even in such situations. This means each electron has a unique position and no two electrons see exactly the same pattern of surrounding charges. Let us consider the atoms in a solid. For example, a silicon crystal. We know that in a crystal, there is a regular arrangement of atoms with constant interplanar spacing between them. The electronic configuration of silicon is 1s2, 2s2, 2p6, 3s2, 3p2. The third orbit, with 4 electrons, is the outermost orbit. Hence, silicon has valency equal to 4. As silicon has a crystalline structure, there are interactions between the neighboring atoms. Let us assume that there are n silicon atoms in the crystal, each with 4 valence electrons. For silicon, in the outermost orbit, there are 8 energy states available, out of which 2 states belong to 3s orbital and 6 states belong to the 3p orbital. Therefore, for n atoms, the total number of energy states available in the outermost orbit is equal to 8n. At the distance between the atoms observed in crystals, such as silicon, these 8n energy states split into 2 levels, each having 4n energy states, due to the atomic interactions discussed earlier. In a crystal, each energy level or state is split up into a large number of closely spaced sublevels. A group of such sublevels with continuous energy variation is called an energy band. For a silicon atom, the lower 4n energy states contain electrons that are in bonding, and such energy states are called the valence band. Therefore, the term valence band refers to a group of energy levels which contains bonded electrons. We know that the electrical conduction in solids takes place by virtue of electrons, which are free to move, that is, by means of free electrons. Since the electrons in the valence band are bonded, they do not contribute to the electrical conductivity of a material. The higher 4n energy states contains those electrons which are free to move about, and as such, they contribute to the electrical conductivity of the semiconducting material. The group of energy levels occupied by such electrons that helps in conduction is called the conduction band. Let EC denote the lowest energy level of the conduction band. Let EV denote the highest energy level of the valence band. The difference between EC and the EV is the energy band gap or energy gap denoted as EG. The valence band electrons can move into the conduction band by gaining energy equal to the energy band gap EG. Thus, there exists a band gap between the lower valence band energy levels and higher conduction band energy levels. For a silicon atom, this energy gap EG is about 1.1 electron volt. This means that for a valence band electron to move in the conduction band, it needs a minimum energy of 1.1 electron volt. At room temperature, we find that a few electrons of the valence band gain thermal energy equal to the energy band gap to move into the conduction band, and hence become free electrons. The vacant energy levels in the valence band create the opportunity of other valence band electrons to move into them. Therefore, in such solids, conduction is possible due to the conduction band electrons, as well as due to the vacancies in the valence band. This is the reason why a semiconductor displays higher conductivity at higher temperatures. However, as the temperature decreases, we find that there are fewer electrons in the conduction band than at higher temperatures, and hence conductivity decreases. At the temperature of 0 Kelvin, the conduction band is practically devoid of any electrons, and as such, there cannot be conduction possible through the semiconductor. Hence, at 0 Kelvin, a semiconductor behaves as an insulator. This is the case of the semiconductor crystal. It is important to note that the band gap is different for different solids. Let us now look at the specific case of solids where the energy band gap EG between the conduction band and valence band is very small, or the conduction band overlaps the valence band. When such an overlap occurs, the band gap EG is nearly zero. In solids where a very small band gap exists, with no external energy available, there are no electrons in the conduction band. When a small energy is supplied, the valence band electrons move into the conduction band. Now let us look at the situation where the conduction band overlaps with the valence band. In this case, the valence band electrons are available to move into the conduction band and thus are readily available for conduction, which happens in the case of metals. Since a large number of electrons are available for conduction, the electrical conductivity is very high for such solids. We know that solids having very high electrical conductivity are called conductors. For some solid, there exists a very large energy band gap greater than 3 electron volt. In such solids, it is practically impossible for the valence band electrons to move into the conduction band, since the energy required is very high as the band gap is very large. Such materials then have very few conduction electrons, and hence have very low electrical conductivity. Such materials are characterized as insulators. In semiconductors, we have seen that a finite but a small band gap of less than 3 electron volt exists, and as such, By supplying sufficient energy, the valence band electrons can move into the conduction band. Therefore, the semiconductors have conductivities between that of the conductors and insulators. Thus, we see that on the basis of energy bands, materials can be classified as conductors, semiconductors, and insulators. With conductors having a very small or nearly zero band gap, semiconductors having a finite and small band gap of less than 3 electron volt, and insulators having a band gap of greater than 3 electron volt. A semiconductor, without any artificially added impurity, is called an intrinsic semiconductor. Both silicon and germanium, the two most commonly used semiconductors, exist as intrinsic semiconductors. Let us take a look at the atomic structure of silicon and germanium. Both silicon and germanium have 4 valence electrons. In crystalline form, each silicon and germanium atom uses its valence electrons to form 4 covalent bonds with 4 surrounding atoms. Let us use the crystal structure of silicon to further study intrinsic semiconductors. Remember, the following discussion applies equally to germanium in its intrinsic form. At absolute zero, all the covalent bonds in the crystal lattice of an intrinsic semiconductor are intact. Thus, at absolute zero, there are no free electrons to occupy the conduction band, and the intrinsic semiconductor behaves like an insulator. However, at higher temperatures, some electrons gain enough thermal energy to break free of the covalent bonds in the crystal lattice. These free electrons move to the conduction band, and the material starts behaving like a semiconductor. Note that each electron that moves to the conduction band leaves behind a vacancy in the valence band. This can be visualized as breaking of a covalent bond, where an electron becomes free and leaves behind a vacancy in the covalent bond. An electron breaking away from a covalent bond takes away a unit negative charge with it, leaving behind a vacancy with an assumed unit positive charge. A vacancy with a unit positive charge in a covalent bond between atoms of a semiconductor is called a hole. Thus, whenever a covalent bond is broken in an intrinsic semiconductor, a free electron and a hole is created. We refer to this as an electron-hole pair. Hence, in an intrinsic semiconductor, the number of free electrons is always equal to the number of holes at any given moment. Consider a hole or a vacancy at position 1 in the crystal lattice of a semiconductor. Now, an electron from position 2 can jump to occupy the vacancy at position 1. This fills the vacancy at position 1 but creates a vacancy or a hole at position 2. Similarly, an electron from position 3 can jump to occupy the vacancy at position 2. This fills the vacancy at position 2 but creates a vacancy or a hole at position 3. As a result of such jumps of electrons across covalent bonds, the holes or vacancies appear to move across the crystal lattice of a semiconductor. Note that the movement of holes occurs because of the movement of electrons across covalent bonds in a semiconductor, and not because of the movement of free electrons. Thus, there are two types of moving charge carriers in the crystal lattice of a semiconductor: the negatively charged free electrons and the positively charged holes. When an electric field is applied across a semiconductor by connecting it across the terminals of a battery, the free electrons move towards the end connected to the positive terminal and generate an electron current denoted by IE. The holes shift towards the end connected to the negative terminal and generate a hole current denoted by IH. The total current flowing through the semiconductor is equal to the sum of the electron current and the hole current. If a free electron collides with a hole, it fills the vacancy in the covalent bond without the generation of any other hole. This is called the process of recombination. Under thermal equilibrium, the rate of generation of free electrons and holes in a semiconductor is equal to the rate of their recombination, so that the density of charge carriers in a semiconductor remains constant. As we learnt earlier, a pure semiconductor without any impurities in it is called an intrinsic semiconductor. Both silicon and germanium exist as intrinsic semiconductors. There are two types of charge carriers in the crystal lattice of an intrinsic semiconductor: the negatively charged free electrons and the positively charged holes. The conductivity of an intrinsic semiconductor increases with rise in temperature, as more number of electrons break away from the covalent bonds of the semiconductor atoms. However, at room temperature, intrinsic semiconductors have very low electrical conductivity. The electrical conductivity of an intrinsic semiconductor can be improved by increasing the number of free electrons or holes in it at room temperature. When a small amount of suitable impurity, say a few parts per million, is added to an intrinsic semiconductor, its conductivity increases to a large extent. A semiconductor that has an added impurity to increase its electrical conductivity is called an extrinsic semiconductor. The process of adding the suitable impurity to a semiconductor is called doping. Thus, an extrinsic semiconductor is also called a doped semiconductor. The impurity atom added to a semiconductor to increase its electrical conductivity is called a dopant. During the process of doping, the dopant gets positioned in the crystal lattice of the semiconductor. It is important that a dopant does not distort the crystal lattice of a semiconductor. For this, the dopant atoms of the semiconductor crystal should be comparable to the semiconductor atoms in size. We have learned that both silicon and germanium are tetravalent. That is, each of their atoms has 4 valence electrons. Commonly used dopants are either trivalent or pentavalent neighbors of silicon and germanium in the periodic table. Commonly used trivalent dopants that have 3 valence electrons are boron, aluminium, and indium. Commonly used pentavalent dopants that have 5 valence electrons are phosphorus, arsenic, and antimony. The addition of trivalent and pentavalent dopants creates two different types of extrinsic semiconductors. We know that in crystalline form, each silicon and germanium atom forms 4 covalent bonds with 4 surrounding atoms. When a trivalent dopant, say an aluminium atom, is added to a silicon semiconductor crystal, the aluminium atom occupies the same position of a silicon atom in the crystal. A trivalent dopant atom forms covalent bonds with 3 neighboring semiconductor atoms. However, the dopant atom has no electron to share with the 4th neighboring semiconductor atom. Thus, a vacancy or hole is created in the lattice. Each trivalent dopant atom creates one hole in the crystal lattice of the semiconductor. At room temperature, some of the electrons break away from their bonds, giving rise to electron-hole pairs. Simultaneously, some of the free electrons recombine with the holes and reduce the number Ni of intrinsically generated electrons to Ne. Thus, the number of holes in a semiconductor doped with a trivalent dopant is much larger than the number of free electrons in it. We learnt earlier that a positive charge is assumed to be associated with holes. Thus, positively charged holes act as majority charge carriers in a semiconductor doped with a trivalent dopant. Thus, such extrinsic semiconductors are called p-type semiconductors. In spite of having the number of holes NH greater than the number of free electrons Ne, the p-type semiconductor crystal remains neutral, as the charge of the additional charge carriers is equal and opposite to that of the ionized cores in the lattice. The movement of holes as charge carriers occurs when valence electrons from neighboring semiconductor atoms jump to fill the holes created by dopant atoms in p-type semiconductors. When a valence electron fills the hole generated by a dopant atom, the dopant atom becomes negatively charged. Thus, a dopant atom in a p-type semiconductor is called a negatively charged core or an acceptor impurity. A p-type semiconductor has an acceptor impurity energy band that lies just above the valence band. Thus, the free electrons can leave the valence band by covering a much smaller energy gap as compared to an intrinsic semiconductor. Valence electrons in p-type semiconductor can move from the valence band to the acceptor impurity energy band even at room temperature to create holes in the lattice. Thus, electrical conductivity of a p-type semiconductor is much better than an intrinsic semiconductor. Now let us see what happens when a pentavalent dopant, say a phosphorus atom, is added to an intrinsic silicon semiconductor crystal lattice. A pentavalent dopant atom in the crystal lattice of the semiconductor forms covalent bonds with 4 neighboring atoms of the semiconductor. The pentavalent dopant atom still has one very loosely bound valence electron that can be set free using a very small amount of energy. Thus, each pentavalent dopant atom contributes a free electron to the crystal lattice of the semiconductor. Therefore, the number of free electrons that are available for conduction by dopant atoms depend largely on the level of doping. If the doping level is high, the number of free electrons contributed for conduction by the dopant increases. This number of free electrons contributed by the donor dopants is not dependent on the temperature of the semiconductor crystal. On the other hand, if the temperature of the crystal is raised, the number of intrinsic electron-hole pairs increase, and this further adds to the conductivity of the crystal. Hence, in a semiconductor doped with pentavalent dopants, the total number of conduction electrons, Ne, is due to the free electrons contributed by the donor atoms, which are pentavalent dopants and those generated intrinsically. But the total number of holes, NH, is only due to the holes from the intrinsic source. Due to the increase in the number of free electrons, the rate of recombination of holes increases. This gives rise to a reduction in the number of holes effectively as compared to the number of free electrons available for conduction. Thus, the number of free electrons in a semiconductor doped with a pentavalent dopant is much larger than the number of intrinsic holes. Negatively charged free electrons act as majority charge carriers in a semiconductor doped with a pentavalent dopant. Thus, such extrinsic semiconductors are called N-type semiconductors. When a dopant atom in an N-type semiconductor gives up a valence electron, it becomes positively charged. Thus, a dopant atom in an N-type semiconductor is called a positively charged core or donor impurity. A N-type semiconductor has a donor impurity energy band that lies just below the conduction band. Thus, electrons can jump to the conduction band by covering a smaller energy gap as compared to an intrinsic semiconductor. Free electrons released by donor impurity atoms in an N-type semiconductor can move from the donor impurity energy band to conduction band even at room temperature. For example, the energy required for an electron to jump from valence band to conduction band in an intrinsic silicon semiconductor is about 1.1 electron volt. If it is doped with a pentavalent impurity to a suitable level and converted to an N-type semiconductor, the energy required for an electron to jump from the valence band to conduction band reduces to 0.05 electron volt approximately. Similarly, if the semiconductor crystal is made of germanium, the energy required for an electron to jump from valence band to conduction band is about 0.72 electron volt. If it is doped with a pentavalent impurity to a suitable level and converted to an N-type semiconductor, the energy required for an electron to jump from the valence band to conduction band reduces to 0.01 electron volt approximately. Thus, electrical conductivity of an N-type semiconductor is much better than an intrinsic semiconductor. It can be shown that at thermal equilibrium, Ne into NH is equal to Ni square. Here, Ne, NH and Ni denote the concentration of electrons, holes, and intrinsic carriers respectively. You will learn about the details of the equation at higher classes. Let us recollect that extrinsic semiconductors are of two types: P-type semiconductors, in which the doping agents are the trivalent impurities, and in which the majority charge carriers are holes, and N-type semiconductors, in which the doping agents are the pentavalent impurities and in which the majority charge carriers are electrons. Consider a p-type semiconductor crystal, to which a specific amount of a pentavalent impurity is added in high concentration. This creates a semiconductor crystal that contains both a p region and an n region. The boundary that separates the p region in the semiconductor from the n region is called the p-n junction. It is important to note that a p-n junction cannot be formed by joining two separate pieces of p-type and n-type semiconductors. Because of the surface irregularities of the two different crystals and because such continuous contact at an atomic level is not possible. If such a junction is formed, the junction would not be continuous and would therefore inhibit the flow of the charge carriers. Now, let us again look at the semiconductor crystal that contains both the p and n regions separated by the p-n junction. We know that in the p region, there is a higher concentration of holes, and in the n region, there is only a smaller concentration of holes. Similarly, in the n region, there is a higher concentration of electrons, and in the p region, there is a smaller concentration of electrons. This causes the holes to diffuse from the p region to the n region across the p-n junction. Physically, this means that some of the valence electrons just to the right of the junction may fill the vacancies just to the left to the junction. Simultaneously, the conduction electrons also diffuses from the n region to the p region across the p-n junction. The ions do not move because of their heavy masses. This diffusion of the majority charge carriers across the p-n junction creates a diffusion current that is directed from the p region towards the n region of the semiconductor. When electrons diffuse from the n region to the p region, they leave behind stationary, positively charged atoms of the donor impurity. Similarly, when holes diffuse from the p region to the n region, they leave behind stationary, negatively charged atoms of the acceptor impurity. This creates a layer of negatively charged ions towards the p side of the p-n junction, and a layer of positively charged ions towards the n side of the p-n junction. The layer of stationary negative charges towards the p side of the junction opposes the diffusion of electrons from the n side. Similarly, the layer of stationary positive charges towards the n side of the junction opposes the diffusion of holes from the p side. This creates an electric field near the junction, which is directed from the n side to the p side. Thus, a small region is created on either side of the p-n junction where no free charge carriers can exist. The region free of moving charge carriers extends on either side of a p-n junction and is called the depletion region. The separation of charges in the depletion region creates a potential difference that opposes the diffusion of electrons in the n region and holes in the p region across the p-n junction. The electrons and holes have to overcome this potential difference, called the barrier potential, to freely diffuse across the p-n junction. The potential difference across the depletion region gives rise to an electric field directed from the layer of positive charges towards the layer of negative charges. The electric field across the depletion region causes electrons in the p region to move to the n region. This is called the electron drift. Simultaneously, the electric field across the depletion region causes the holes in the N region to move to the P region. This is called the hole drift. This drift of minority charge carriers across the p-n junction creates a drift current that is directed from the N region towards the P region of the semiconductor. Thus, we observed that the diffusion current and the drift current across a p-n junction are opposite in direction. We have to remember that at the time of formation of the p-n junction, there is no depletion region. Thus, there is a high diffusion current but no drift current. As the depletion region gets formed, the diffusion current decreases and the drift current increases. In steady state, the diffusion current and drift current become equal in magnitude and there is no transfer of charge at any cross-section. Thus, a crystal with p-n junction in an isolated state is electrically neutral. A p-n junction with metallic contacts provided at its ends forms a basic semiconductor device called a diode. A diode is represented by the symbol shown here. Semiconductor diodes are the fundamental components of most of the electronic gadgets we use in our daily lives. We have learnt that in a diode with metallic contacts, there is a p-n junction, separating the p side from the n side, and a depletion region which is devoid of any charge carriers. The holes are the majority charge carriers in the p side, and the electrons are the majority charge carriers in the n side. We have also learnt that when the diode is not connected to the battery, the n side is at a higher potential and the p side is at a lower potential, and the diffusion current and drift current across the p-n junction are opposite in direction and equal to each other at equilibrium. It is important to note that the diffusion current is due to the movement of majority carriers of the p and n regions from one side to the other. Similarly, the drift current is due to the minority charge carriers of the p and n regions from one side to the other side. In this situation, the separation of charges in the depletion region creates a barrier potential that opposes the diffusion current across the p-n junction. We know that the barrier potential prevents any further movement of charges across the junction. Now, let the p-n junction diode be connected to a battery such that the p side is connected to the positive terminal and the n side is connected to the negative terminal of the battery. When connected in this way, the diode is said to be forward biased. When a p-n junction diode is in forward bias, the potential of the p side is raised and now the p side is at a higher potential and the n side is at a lower potential. Due to the forward bias connection, the barrier potential across the p-n junction decreases and becomes equal to the difference between the barrier potential V0 at equilibrium and the external applied voltage V. Also, when a diode is forward biased, the width of the depletion region around the p-n junction decreases. The lowering of the barrier potential and the decrease in the width of the depletion region leads to an increase in the diffusion of electrons from the n side to the p side. Simultaneously, the diffusion of holes from the p side to the n side across the p-n junction also increases. Since holes and electrons are the minority charge carriers in the N region and P region respectively. This increased diffusion of charge carriers in a forward-biased diode is also called minority carrier injection. As a result of the minority carrier injection in a forward-biased diode, the diffusion current increases much above its equilibrium value. But the drift current remains almost unaffected since the rate of formation of whole electron pairs is almost constant and is independent of the electric field applied by the battery. Thus, the diffusion current exceeds the drift current, and a net current flows from the P side to the N side in a forward-biased diode. The net diode forward current is equal to the sum of the whole diffusion current and the conventional current due to electron diffusion. This current is in the milliampere range. The net current flowing through a forward-biased diode can be measured using the circuit shown here. The diode D is forward-biased using the battery B. The diode forward current can be measured using the milliammeter MA. The potential difference across the junction is measured using a voltmeter V. The voltage across the junction can be varied using the rheostat RH. The graph showing the variation of current versus potential difference for a forward-biased diode is called its VI characteristics. The origin is the position of equilibrium when no external voltage is applied across a diode and no net current flows through it. The net current in a forward-biased diode remains zero or negligible until the external applied voltage reaches a certain threshold value. Beyond the threshold value, the net current in a forward-biased diode increases rapidly for small increases in the externally applied voltage. If the current increases beyond the rated value, it can get damaged unless it is protected. The current I in the circuit changes non-linearly with the applied potential difference, and hence the diode is said to be non-ohmic in nature. Now let us study about the reverse bias connection of a PN junction diode. For this, connect a PN junction diode to a battery such that the P side is connected to the negative terminal and the N side is connected to the positive terminal of the battery. Here, the P side of the diode is at a lower potential and the N side of the diode is at a higher potential since the battery raises its potential more than its value for the unbiased state. When a diode is reversed biased, the barrier potential across its PN junction increases and is given by the sum of the barrier potential V0 at equilibrium and the externally applied voltage V. Also, when a diode is reverse biased, the width of the depletion region around the PN junction increases. The increase in barrier potential width of the depletion region leads to a decrease in the diffusion of holes from the P side to the N side and the electrons from the N side to the P side across the junction. Thus, in a reverse biased diode, the diffusion current decreases much below its equilibrium value, while the drift current remains unaffected. The drift current is now greater than the diffusion current. Hence, a net current flows from the N side to the P side in a reverse biased diode. The net current is small as the drift current itself is small, and hence the net current is even smaller. The net current flowing through a reverse biased diode is of the order of a few microamperes and can be measured using the circuit shown here. In the circuit diagram, the current in the circuit is measured using the microammeter. The potential difference across the junction is measured using a voltmeter V, and the applied potential difference to the diode can be varied using a rheostat RH. The diode is connected to the terminals of the battery such that its P side is now connected to the negative terminal of the battery, and the N side of the diode is connected to the positive terminal of the battery. The graph showing the variation of current versus potential difference for a reverse biased diode is called its VI characteristics for reverse bias. Under reverse bias, the net current, called the reverse saturation current, does not vary much, with increasing applied voltage, and is almost constant for small reverse bias voltages, until the applied voltage to the diode becomes equal to a certain voltage, VBR, known as breakdown voltage or cut-in voltage. When the applied diode voltage becomes equal to the threshold voltage or the cut-in voltage, the current in the circuit increases suddenly to very large values, causing a lot of heat to be produced in the diode, and hence the diode can get damaged unless we adopt some precautionary measures. Typically, the threshold voltage is nearly 0.2 volt for a germanium diode and 0.7 volt for a silicon diode. The VI characteristics of a diode in forward bias and reverse bias are shown on the same graph for a comparison between them. We observe that a diode allows a large amount of current to flow when forward biased. In reverse bias, diode allows a very small amount of current to flow, unless it is operated in the breakdown region. Thus, a diode is a device that allows free flow of electric current, or we say conducts, in only one direction when it is in forward bias. It allows little or no current to flow, or we say does not conduct, in the opposite direction when it is in reverse bias. We can also say that a forward biased diode offers low resistance, while a reverse biased diode offers high resistance to the flow of electric current. A diode is said to offer dynamic resistance that changes with applied voltage. The dynamic resistance R of a diode is given by a small change in applied voltage delta V divided by a corresponding small change in current delta I. We know that if we connect a PN junction diode to a battery with the P side connected to the negative terminal and the N side connected to the positive terminal, the diode is said to be reverse biased. A reverse biased diode allows little or no current through it. According to the IV characteristic of a PN junction diode, the current through a reverse biased diode changes very little with an increase in applied voltage, and it remains almost constant. The value of this current is called the reverse saturation current. Let us see what happens when we increase the applied voltage across a reverse biased diode after it attains the reverse saturation current stage. We observe that the current through the reverse biased diode suddenly increases for a specific value of applied voltage. This phenomenon is called breakdown of the diode. Diode breakdown occurs because a high applied voltage creates a strong electric field that results in the breakage of covalent bonds in the p region. The electrons released by this breakage of bonds have enough energy to enter the n region, resulting in a large increase in current through the diode. The emission of these electrons from the host atoms due to the high applied voltage is called the internal field emission or field ionization. The voltage at which there is a sudden increase in current in a reverse biased diode is called the breakdown voltage. A diode designed to have low breakdown voltage under reverse bias is called a ZENER diode, which is named after its inventor ZENER. A ZENER diode is made by doping both the p and n sides of a p-n junction diode heavily. The circuit symbol of a ZENER diode is represented as shown. Although it is similar to that of a p-n junction diode, the major difference is that the two small projections in opposite directions are added to the line on the n side of the p-n junction circuit symbol. The pointed edge of the triangle indicates the n side of the diode, and the base of the triangle indicates its p side. Beyond the breakdown voltage, even an insignificant change in the reverse bias voltage can produce a significantly large change in the current. This implies that the voltage across the ZENER diode remains constant, even though the current through it varies widely. Thus, a ZENER diode can be used as a voltage regulator to convert a variable voltage input into a constant voltage output. Here is a simple circuit used for converting a variable voltage input, say, from a rectifier into a constant voltage output using a ZENER diode. The input voltage is connected to the ZENER diode through a series resistor having resistance R with the ZENER diode in a reverse bias arrangement. A load resistance is connected parallel to the ZENER diode to collect the constant voltage output across it. The current through R is equal to the sum of the ZENER current and load current. If the input voltage in the circuit is increased, the current through R and the ZENER diode increases. This causes an increase in voltage across R without a change in voltage across the ZENER diode. This is due to the fact that beyond the breakdown voltage, the voltage across the ZENER diode remains the same, although the current through it changes. On the other hand, if the input voltage is decreased, the current through R and the ZENER diode decreases. This reduces the voltage across R without affecting the voltage across the ZENER diode. Thus, irrespective of increase or decrease in the input voltage, the voltage across the ZENER diode remains constant, which is collected across the load resistance. Hence, the ZENER diode acts like a voltage regulator. The choice of the ZENER diode depends on the required output voltage. ZENER diodes are available with output voltages ranging from a few volts to hundreds of volts. In order to provide good voltage regulation, it is essential that the current through the ZENER diode is several times higher than the load current. This is done by selecting a suitable series resistance R that ensures ZENER current in the circuit is several times higher than the load current. Optoelectronic junction devices are PN junction devices which work because of the current carriers that are generated by photons. Photodiodes, light-emitting diodes, which are referred to as LEDs in short, and solar cells are examples of optoelectronic devices. A photodiode is a device that is used to detect optical signals. It is a photodiode in your TV set that allows you to operate your TV using a remote. A photodiode is a specially fabricated PN junction diode with a transparent window that allows light to be incident on the diode. We know that light consists of tiny bundles of energy called photons, whose energy in turn depends on the frequency of the light. We also know that electrons in the semiconductor atoms of a diode need to overcome an energy gap to become free and create electron-hole pairs that act as charge carriers in the diode. When photons of light with energy greater than the energy gap fall on the diode, the photons get absorbed by the semiconductor atoms, leading to the creation of electron-hole pairs in the diode. A photodiode is designed so that the maximum number of electron-hole pairs is created in the depletion region around the PN junction. We know that the depletion region has an electric field created due to the separation of static charges on both sides of the PN junction. As soon as an electron-hole pair is created, the electric field across the depletion region pushes the hole towards the P side and the electron towards the N side. Due to this movement of charge carriers, a small photocurrent is generated through an external load connected across a photodiode. The magnitude of the photocurrent increases with an increase in the intensity of the incident light. However, this change is too small to be measured in the absence of any external bias. The magnitude of the photocurrent is too small compared to the large current that flows through the diode under forward bias. Thus, the change in photocurrent with change in the intensity of light is very difficult to measure when a diode is operated under forward bias. However, the change in the magnitude of the photocurrent with the intensity of the incident light can be measured when a small current flows through the diode under reverse bias. Thus, a photodiode is always operated under reverse bias. The IV characteristics of a reverse-biased photodiode for different intensities of incident light are shown here. A light-emitting diode, or an LED, is a device that produces photons of different frequencies of light. An LED is a specially fabricated, heavily doped PN junction diode encased in a transparent cover which allows the emitted light to shine through. An LED is operated under forward bias, which increases the diffusion of minority charge carriers across the PN junction. This leads to the recombination of the electron-hole pairs, which results in the liberation of energy in the form of photons. The energy of the emitted photons and the color of the light produced depends on the nature and the band gap of the semiconductor material used in the LED. Here is a list of some semiconductor materials used in LEDs of different colors. LEDs offer several advantages listed here over conventional electrical light sources: low operational voltage and power consumption, instant on-off switching without any warm-up time, source of near monochromatic light, long life and negligible wear and tear. LEDs have low reverse bias breakdown voltages. Thus, care must be taken that they do not get connected in reverse bias across a high voltage source. Now let us consider a solar cell. A solar cell is a device that converts light energy into electrical energy. The solar panels that you see connected to solar power appliances are made of a large number of individual solar cells. A solar cell consists of a thin, flat wafer of P-type semiconductor on which a very thin layer of N-type semiconductor is grown to create a p-n junction with a large surface area. The back of the P side is coated with a metal to form a metallic back contact. The top of the N side is provided with a metallic grid contact that covers only a small percentage of the total exposed area of the cell. A solar cell works when light is incident on it from the top over the N side of the device. A solar cell works on the same principle as that of a photodiode, where incident light generates electron-hole pairs in the depletion region of the p-n junction. As in a photodiode, the holes are pushed towards the P side and electrons are pushed towards the N side due to the electric field in the depletion region of the solar cell. The holes pushed towards the P side are collected by the back contact, while the electrons pushed towards the N side are collected by the grid contact. This collection of charges makes the back contact positive and the grid contact negative and gives rise to a current when a load is connected between the two. Unlike a photodiode, a solar cell works without any external bias. The large surface area of the p-n junction in a solar cell generates measurable photocurrent, making it a source of electricity. However, just like a photodiode, the photocurrent produced by a solar cell depends on the intensity of the incident light. If we plot the intensity of solar radiation against its energy, we find that the maximum intensity radiation is produced by photons having energy equivalent to 1.5 electron volts. Thus, semiconductors having band gaps lower than 1.5 electron volts are used in the manufacturing of solar cells. Here are a few examples. In semiconductors having band gaps higher than 1.5 electron volts, only a small portion of the total solar radiation is used to produce photocurrent. Thus, such materials are not preferred in the making of the solar cells. In semiconductors having band gaps much lower than 1.5 electron volts, most of the incident radiation is absorbed by the top layer of the cell. Thus, very little radiation reaches the depletion region to produce electron-hole pairs that gives rise to the photocurrent. Hence, such materials are also not preferred in the making of the solar cells. Besides band gap, the other criteria for selection of suitable material for solar cells include high solar radiation absorption capability, good electrical conductivity, and ease of availability and cost. Here, we can see the IV characteristic of a solar cell which is drawn in the fourth quadrant, as it does not require any external bias and acts as a source of electricity. A transistor is a semiconductor device used for switching and amplifying electric signals. A point contact transistor was invented by J. Bardeen and Walter Brattain in 1947. The first junction transistor was invented by William Shockley in 1951. There are many different kinds of transistors. However, in this module we will discuss the transistors that contain two back-to-back p-n junctions. Such transistors are called bipolar junction transistors, referred to as BJT in short. When we speak about transistors in general, without reference to any particular kind, we refer to these bipolar junction transistors. There are two types of bipolar junction transistors: the PNP transistor and the NPN transistor. A PNP transistor consists of a smaller, heavily doped P region and a larger, moderately doped P region separated by a thin, lightly doped N region. An NPN transistor consists of a smaller, heavily doped N region and a larger, moderately doped N region separated by a thin, lightly doped P region. The smaller, heavily doped region in a PNP or in an NPN transistor is called the emitter. The emitter supplies a large number of majority charge carriers that are holes in a PNP transistor and electrons in an NPN transistor. The larger, moderately doped region in a PNP or in an NPN transistor is called the collector. The collector collects the major portion of the majority charge carriers provided by the emitter. The thin, lightly doped region in a PNP or in an NPN transistor that separates the emitter and collector is called the base. Connecting terminals are provided for the emitter, the collector, and the base. Thus, a transistor is a three-terminal device. Suitable potential difference must be applied across both the p-n junctions to operate a transistor. This process is called biasing the transistor. To bias the two p-n junctions in the transistor, we require a pair of terminals for each p-n junction. Thus, in total, we require 4 terminals. But the transistor has only 3 terminals. Hence, one of the terminals is made a common terminal to bias the two p-n junctions. The emitter, or the base, or the collector can act as the common terminal, and biasing on this information, the configuration of the transistor is named accordingly. In this module, we discuss about transistors in common base configuration. During biasing, normally the p-n junction between the emitter and the base is forward biased, while the p-n junction between the base and the collector is reverse biased. The reasons for adopting such a biasing scheme for the two junctions will be discussed at the appropriate juncture in the course. A transistor with its emitter base junction forward biased and base collector junction reverse biased is said to be in an active state. Before we discuss the working of PNP and NPN transistors in the active state, let us recall that by convention, the direction of electric current is taken opposite to the direction of the flow of electrons, that is, in the same direction of the flow of holes. When the emitter base junction of a PNP transistor is forward biased, a large number of holes from the emitter enter the base, This large flow of holes from the emitter to the base constitutes the emitter current. This current is equal to the current entering the emitter from the emitter terminal connected to the battery. Since the base is very thin and the base collector junction is reverse biased, most of the holes entering the base reach the collector terminal, forming the collector current. Only a very small portion of the holes entering the base reach the base terminal, forming a small base current. A PNP transistor is represented by the symbol as shown. Note that the direction of the arrow indicates that in a PNP transistor, current is directed from the emitter to the base. Similarly, when the emitter-base junction of an NPN transistor is forward biased, a large number of electrons from the emitter enter the base. This large flow of electrons from the emitter to the base constitutes the emitter current, opposite in direction to the flow of electrons. This current is equal to the current leaving the emitter from the emitter terminal connected to the battery. Since the base is very thin and the base collector junction is reverse biased, most of the electrons entering the base reach the collector terminal constituting the collector current. Only a very small portion of the electrons entering the base reach the base terminal, forming a small base current. An NPN transistor is represented by the symbol as shown. Note that the direction of the arrow indicates that in an NPN transistor, current is directed from the base to the emitter. As per Kirchhoff's law, in both PNP and NPN transistors, the emitter current is equal to the sum of the base current and collector current. Note that in both cases, the base current is very small compared to the emitter current. Thus, the emitter and the collector currents are nearly equal. In the circuits we discussed so far about transistors in the common base configuration. We will discuss later about different types of configurations and their uses. You have learned that there are two types of bipolar junction transistors, namely the PNP transistors and the NPN transistors. You have also learned that a transistor is said to be in active state when its emitter-base junction is forward biased and base collector junction is reverse biased. While biasing a transistor, the forward biased connection is called the input circuit and the reverse biased connection is called the output circuit. Since a transistor is a three-terminal device, one of its terminals is common to both input and output. This gives rise to three transistor circuit configurations. When the base of a transistor is common to the input and output, the transistor is said to be in the common base configuration. In this case, the input voltage is represented as VEE and the output voltage is represented as VCC. When the emitter of a transistor is common to the input and output, the transistor is said to be in the common emitter configuration. In this case, the input voltage is represented as VBB and the output voltage is represented as VCC. When the collector of a transistor is common to the input and output, the transistor is said to be in the common collector configuration. In this case, the input voltage is represented as VBB and the output voltage is represented as VEE. Since the NPN silicon transistor is the most commonly used transistor and the common emitter configuration is the most commonly used circuit configuration, let us study the input and output characteristics of an NPN transistor in the common emitter configuration. The circuit to study the input and output characteristics of an NPN transistor in the common emitter configuration is as shown. In the common emitter configuration, the input is between the base and the emitter, and the output is between the collector and the emitter. The variation of base current, IB, with the base emitter voltage, VBE, is referred to as the input characteristics, and the variation of collector current, IC, with the collector emitter voltage, VCE, is referred to as the output characteristics. The input characteristics of an NPN transistor in the common emitter configuration can be studied by plotting the base current, IB, against the base emitter voltage, VBE, at a constant collector emitter voltage, VCE. The collector emitter voltage, VCE, is kept constant within the range of 3 volts to 20 volts to ensure that the collector base junction is reverse biased and the transistor is in active state. Since the common emitter voltage, VCE, is the sum of the common base voltage, VCB, and the base emitter voltage, VBE, and the base emitter voltage, VBE, is 0.6 volts for a silicon transistor, the collector emitter voltage is sufficiently larger than 0.6 volts. An increase in the collector emitter voltage, VCE, appears with an increase in the collector base voltage, VCB, keeping the base emitter voltage, VBE, constant. Thus, the effect on the base current, IB, is negligible. Hence, the different constant values of the collector emitter voltages, VCE, gives almost identical curves for the input characteristics. The input characteristics can be used to calculate the input resistance. The input resistance, Ri, is defined as the ratio of the change in the base emitter voltage, delta VBE, to the resulting change in the base current, delta IB, at a constant collector emitter voltage, VCE. The input resistance is referred to as a dynamic resistance and is of the order of a few hundred ohms to a few thousand ohms. The output characteristics of an NPN transistor in common emitter configuration can be studied by plotting the collector current, IC, against collector base voltage, VCE, at a constant base current, IB. Since the base emitter junction is in forward bias, a small increase in the base emitter voltage, VBE, increases the hole current from the emitter and the electron current from the base. As a result, the base current, IB, and the collector current, IC, increase proportionately. Thus, the different constant values of the base current, IB, give different output characteristics as shown here. The output characteristics can be used to calculate the output resistance. The output resistance, RO, is defined as the ratio of the change in the collector emitter voltage, delta VCE, to the change in the collector current, delta IC, at a constant base current, IB. Since the base collector junction is reverse biased, the output resistance is very high and is of order of a few hundred kilo ohms. The current amplification factor, beta, of a transistor is defined as the ratio of the change in the collector current, delta IC, to the change in base current, delta IB, at a constant collector emitter voltage, VCE. The AC current amplification factor is also known as the small signal current gain. Its value is very large since a large change in the collector current results in a very small change in the base current. The ratio between the absolute values of the collector current IC and the base current IB is called the DC current amplification factor. The values of the AC current amplification factor and the DC current amplification factor are almost equal. You have learned that when the emitter terminal of a transistor is common to the input and the output, the transistor is said to be in common emitter configuration. For a transistor in common emitter configuration, the forward-biased emitter-base junction forms the input circuit, where the input voltage is VBB, while the reverse-biased collector-emitter junction forms the output circuit, where the output voltage is VCE. We shall try to understand the operation of the transistor as a switch by analyzing the behavior of the base-biased NPN transistor in the common emitter configuration. On applying Kirchhoff's voltage rule to the input of the circuit, we get VBB is equal to IB into RB plus VBE. Let this be equation 1. And, on applying Kirchhoff's voltage rule to the output of the circuit, we get VCE is equal to VCC minus IC into RC. Let this be equation 2. Here the input voltage VBB is represented with VI and the output voltage VCE is represented with VO. Then the equation 1 can be written as VI is equal to IB into RB plus VBE. Let this be equation 3. And the equation 2 can be written as VO is equal to VCC minus IC into RC. Let this be equation 4. Let us now discuss the change in the output voltage VO with the change in the input voltage VI. In case of a silicon transistor, the cutoff voltage is 0.6 volts. As long as the input voltage VI is less than 0.6 volts, the transistor is in the cutoff state and the collector current IC is 0. Then from equation 4, the output voltage VO is equal to VCC. When the input voltage VI becomes greater than 0.6 volts, the transistor goes into the active state. In the active state of the transistor, the collector current IC increases linearly with increase in input voltage VI. Then, the output voltage VO is equal to VCC minus IC into RC. The output voltage VO decreases linearly till its value becomes less than 1 volt. Beyond this, the transistor goes into the saturation state. That is, with further increase in input voltage VI, the output voltage further decreases to 0 but never becomes 0. In the saturation state of the transistor, the collector current IC is maximum. Let us now discuss about the transistor as a switch. When the input voltage VI is low, the transistor is in the cutoff region. In the cutoff region, the collector current IC is 0 and it is not conducting. Then it is said to be switched off. If the input voltage Vi is high enough to drive the transistor into saturation state, the output is low and very near to zero, and the collector current IC is maximum. Then it is said to be switched on. Let us now discuss about the transistor as an amplifier. To discuss the transistor as an amplifier, we use the active state of the transistor. In the active region of the transistor, the output voltage VO decreases linearly with an increase in the input voltage Vi. If delta Vi and delta Vo are the small changes in the input voltage and the output voltage, then the ratio of the change in output voltage to the change in input voltage is called small signal voltage gain. That is, AV is equal to delta VO by delta Vi. Let this be equation 5. When the input voltage Vi is at the midpoint of the active region, then the circuit behaves as a common emitter amplifier with voltage gain AV. This voltage gain AV can be expressed in terms of the resistances in the circuit and the current gain of the transistor. We know that the current gain of the transistor, beta AC, is equal to delta IC by delta IB. Let this be equation 6. From equation 4, we can write the small change in output voltage delta VO is equal to 0 minus RC into delta IC, which is equal to minus RC into delta IC. Let this be equation 7. Similarly, from equation 3, the small change in voltage delta Vi is equal to RB into delta IB plus delta VBE. But delta VBE is negligibly small in the circuit. Then delta Vi is equal to RB into delta IB. Let this be equation 8. On substituting equations 7 and 8 in equation 5, we get AV is equal to minus RC into delta IC by RB into delta IB. Let this be equation 9. On substituting equation 6 in equation 9, we get the voltage gain of the amplifier as AV is equal to minus beta AC into RC by RB. Thus, the transistor in the active region can be used as an amplifier. You have learnt that when a transistor is in the active state, a small increase in the base current IB causes a large corresponding increase in the collector current IC. Thus, a transistor in the active state behaves like an amplifier. The operating point of a transistor as an amplifier is fixed somewhere in the middle of the active region. We know that the current amplification factor, beta AC, is equal to beta DC. That is equal to delta IC by delta IB. Let this be equation 1. And the voltage gain AV is equal to delta VO by delta VI. Let this be equation 2. These expressions are applicable to the transistor as an amplifier of DC voltage. Now let us look at the transistor as an amplifier of AC voltage. An AC sinusoidal wave representing input voltage Vi superimposes over the supply voltage VBB for the base emitter circuit. The input AC voltage VI causes sinusoidal variations in the base current IB. The sinusoidal variations in the base current IB introduce corresponding sinusoidal variations in the collector current IC. The sinusoidal variations in collector current IC produces corresponding changes in the output voltage VO, which can be measured across the battery VCC and the resistance RC. Large capacitors are used to block the DC voltages while measuring the AC variations across the input and output terminals. Let us now derive an expression for AC voltage gain in the transistor amplifier. Initially, let us assume the input voltage VI is equal to 0, and, applying the Kirchhoff's law to the output part of the circuit, we get VCC is equal to VCE plus IC into RC. Let this be equation 3. Similarly, applying the Kirchhoff's law to the input part of the circuit, we get VBB is equal to VBE plus IB into RB. Let this be equation 4. When the input AC voltage VI is not 0, we get the sum of VI and VBB as VBE plus IB into RB plus delta IB into RB plus RI. Let this be equation 5, where Ri in equation 5 is the internal resistance of the input circuit, which is equal to delta VBE by delta IB. From equations 4 and 5, we can write the input voltage VI is equal to delta IB into RB plus RI. The input voltage VI can be written as VI is equal to delta IB into R. Let this be equation 6, where R is equal to RB plus RI. On rearranging equation 3 for the output circuit, we get VCE is equal to VCC minus IC into RC. Let this be equation 7. Thus, a small change in VCE, delta VCE is equal to delta VCC minus delta IC into RC. Let this be equation 8. Since VCC is fixed, delta VCC is equal to 0. Thus, a small change in VCE is given as minus delta IC into RC. The change in VCE is equal to output voltage VO. Then, VO is equal to minus delta IC into RC. Let this be equation 9. The AC voltage gain AV is the ratio of output voltage VO to the input voltage VI. Substituting the values of VI and VO from equations 6 and 9 in the equation for AC voltage gain, we get AV is equal to minus delta IC into RC by delta IB into R. Let this be equation 10. We know that the current amplification factor beta AC is equal to delta IC by delta IB. On substituting the current amplification factor in equation 10, we get the AC voltage gain AV is equal to minus beta AC into RC by R. Let this be equation 11. Then the AC power gain in a transistor amplifier is equal to the product of the current amplification factor and voltage gain. That is, AP is equal to beta AC into AV. Note that a transistor does not generate power. It just uses the power from the batteries in its input and output circuits to amplify an AC signal. An oscillator is an electronic device that converts DC voltage into AC voltage. An oscillator consists of a transistor amplifier and a feedback network that extracts a part of the output of the amplifier and feeds it back as input to the transistor amplifier. A commonly used feedback network consists of an LC circuit formed by the combination of an inductor with inductance L and a capacitor with capacitance C. This is a resonant circuit that produces an output of a particular resonant frequency. A simple circuit used to understand a transistor oscillator is shown here. The circuit contains an NPN transistor in the common emitter configuration, with the base emitter junction forward biased and the base collector junction reverse biased. The input circuit of the transistor is connected to a coil T1 across terminals 1 and 2. The output circuit of the transistor is connected to a coil T2 across terminals 3 and 4. Note that coil T2 forms a part of the LC circuit used for the feedback network. Coils T1 and T2 are wound on the same core so that they can influence current in each other through inductance. The output circuit also contains a switch S. When the switch is open, the transistor cannot conduct and is in the cutoff state. When the switch S is closed, the collector current rises from 0 to a peak value as shown in the graph. As the collector current rises in coil T2, it induces a current in coil T1. Due to this inductance or positive feedback from coil T2 to coil T1, the emitter current also rises to a peak value as shown in the graph. When the inductor current reaches the peak or becomes maximum, it stops rising further and the transistor goes into the saturation state. When the transistor goes into the saturation state, the current stops changing in coil T2 and therefore inductance or feedback from coil T2 to coil T1 stops. When the inductance or feedback from coil T2 to coil T1 stops, emitter current starts decreasing. As the emitter current decreases, the collector current also starts decreasing. The decreasing collector current in coil T2 sends a negative feedback through induction to coil T1. The negative feedback further decreases the emitter current and the collector current till both become 0. At this stage, the transistor is back to the cutoff state. From the cutoff state, the transistor moves to saturation state and back. The cycle continues, giving rise to an AC output. The frequency of the AC output voltage is equal to the resonant frequency of the LC circuit formed by the inductance L of coil T2 and the capacitance C. Since the LC circuit is connected on the collector side of the common terminal, this form of an oscillator circuit is called the tuned collector oscillator. You have already learned that when the P side of a PN junction diode is connected to the positive terminal of a battery and the N side is connected to its negative terminal, the diode is said to be forward biased. And when the P side of a PN junction diode is connected to the negative terminal and the N side is connected to the positive terminal, the diode is said to be reverse biased. You have also learned that a diode allows free flow of electric current under forward bias, but allows little or no current to flow under reverse bias. This property allows a diode to work as a rectifier. A rectifier is a device that converts alternating current into direct current. Now, let us consider a circuit in which an AC input is connected to the primary coil of a step-down transformer. A diode is connected in series with a load resistance R across the ends S1 and S2 of the secondary coil of the transformer as shown. Due to the AC input, S1 is positive and S2 is negative for the positive half cycle, while in the negative half cycle, S1 is negative and S2 is positive. Thus, the direction of voltage applied across the diode keeps changing. When S1 is positive and S2 is negative, the diode is forward biased and allows current to flow through it. Thus, during the positive half cycle, current flows through the load resistance and we get a voltage output across R as shown. When S1 is negative and S2 is positive, the diode is reverse biased and allows negligible current to flow through it. This current is so small that it is considered to be equal to zero. Thus, during the negative half cycle, no current flows through the load resistance and we do not get any voltage output across R. Here, the diode produces a pulsating voltage across the load resistance R. Since the output voltage is only in one direction, it is called rectified output. Since this circuit produces rectified output only for the positive half cycle of the AC wave, it is called a half-wave rectifier. Now consider the circuit as shown, in which an AC input is connected to the primary coil of a step-down transformer. The ends S1 and S2 of the secondary coil are connected to the P sides of two diodes whose N sides are connected to each other. The load resistance R is connected across the N sides of the two diodes and the center tap C is provided at the middle of the secondary coil. The potential at S1 and S2 changes with the AC input cycle. When S1 is positive and S2 is negative, diode 1 is forward biased and allows current to flow through it. However, at the same time, diode 2 is reversed biased and does not allow current to flow through it. Thus, during the positive half cycle, current flows through the load resistance R via diode 1 and the center tap C, and we receive a voltage output across R. When S1 is negative and S2 is positive, diode 1 is reversed biased and does not allow any current to flow through it. However, at the same time, diode 2 is forward biased and allows current to flow through it. Thus, during the negative half cycle, current flows through the load resistance R via diode 2 and center tap C, and we receive a voltage output across R. Thus, a combination of the two diodes produces more continuous pulses of rectified voltage across the load resistance R. Since this circuit produces rectified output for both the positive and the negative half cycles of the AC wave, it is called a full-wave rectifier. Although the output of a full-wave rectifier is more continuous than a half-wave rectifier, it is still in the form of unsteady pulses of voltage. A more steady output can be received from a rectifier by connecting a suitable capacitor in parallel with the load resistance. The capacitor prevents a signal can be made of discrete values of current or voltage, as in a digital signal. A digital signal can only have a low and a high value of current or voltage represented by the numbers 0 and 1 respectively. Thus, digital signals consist of strings of zeros and ones called binary numbers. The circuits that control the flow of digital signals on the basis of a logical relationship between the input and output signals are called logic gates. The 5 commonly used logic gates are the AND, OR, NOT, NAND, and the NOR gates. Let us use simple circuits of one or more switches and a bulb to understand logic gates. Here, the state of the switch is the input that determines the state of the bulb that represents the output. An open switch represents an input of 0. The bulb remains off in this condition and represents an output of 0. A closed switch represents an input of 1. The bulb lights up in this condition and represents an output of 1. Now here is a circuit representing an AND gate. An AND gate has 2 or more inputs. The 2 switches A and B represent 2 inputs and the bulb O represents the output of the logic gate. Let us list all the possible input and output combinations of an AND gate in a table. When both the switches A and B are open, no current flows from them, so both the inputs are 0. The bulb in this case remains off, hence the output is also 0. When switch A is closed and switch B is open, input A is 1, while input B is 0. The bulb in this case still remains off, hence the output is still 0. When switch A is open and switch B is closed, input A is 0, while input B is 1. The bulb in this case again remains off, hence the output is again 0. When both the switches A and B are closed, both the inputs A and B are 1. The bulb in this case turns on, indicating this time that output is 1. An AND gate is represented by the symbol shown here. The table that lists all the logical input and output combinations of a logic gate is called the truth table of the logic gate. Thus, the table shown here is the truth table of the AND gate. The output of an AND gate is 1 only when inputs A and B are both 1. Now let us learn about the OR gate. Here is a circuit representing an OR gate. Just like an AND gate, an OR gate also has 2 or more inputs. Let us form the truth table of the OR gate. When both the switches A and B are open, no current flows from them, so both the inputs are 0. The bulb in this case remains off. Hence, the output is also 0. When switch A is closed and switch B is open, input A is 1, while input B is 0. The bulb in this case turns on. Hence, the output is 1. When switch A is open and switch B is closed, input A is 0, while input B is 1. The bulb in this case again turns on. Hence, the output is again 1. When both switches A and B are closed, both the inputs A and B are 1. The bulb in this case yet again turns on. Hence, the output is again 1. The symbol and the truth table of an OR gate are shown here. The output of the OR gate is 1 when either input A or input B or both are 1. Now, here is a circuit representing a NOT gate. Unlike the AND and OR gates, a NOT gate has only one input represented by switch A. Let us form the truth table of the NOT gate. When switch A is open, no current flows from it, so the input is 0. However, the bulb is turned on, hence the output is 1. When switch A is closed, assuming 0 resistance in the switch, all current flows through the switch and no current flows through the bulb. Thus, input is 1 and output is 0. The symbol and the truth table of a NOT gate are shown here. From the truth table, we can see that a NOT gate inverts the input. Thus, it is also called an inverter gate. An AND gate followed by a NOT gate forms a NAND gate. The symbol of a NAND gate is a combination of symbols of the AND and NOT gates as shown here. Note that in a NAND gate, the output of the AND gate acts as the input for the NOT gate. The output of the AND gate is inverted by the NOT gate and appears as the output of the NAND gate. Hence, if inputs A and B are both 1, the output of NAND gate is not 1. An OR gate followed by a NOT gate forms a NOR gate. The symbol for a NOR gate is a combination of symbols of the OR and NOT gates as shown here. In a NOR gate, the output of the OR gate acts as the input for the NOT gate and thus gets inverted. Thus, the input values in the truth table of a NOR gate are taken from the input values from the OR gate table. The output of the OR gate is inverted by the NOT gate and appears as the output of the NOR gate. NAND and NOR gates are also called universal gates, as they can be used to create all other forms of logic gates like the AND, OR, and NOT gates. Logic gates in a circuit are realized by combinations of electronic devices.
दोस्तों, यदि आज की वीडियो आपको अच्छी लगी हो तो लाइक कीजिए, चैनल को सब्सक्राइब कीजिए और अपने दोस्तों के पास इस वीडियो को शेयर कीजिए। अगर आपका कोई कमेंट हो तो कमेंट बॉक्स में नीचे जरूर लिखिए। थैंक यू।